Hello, everybody. Welcome to my second session here of the lectures for Math 2130 as we try to work through the last little bit of the material before our global interruption, I suppose. Um, we're going to be covering our next technique for numerical integration today, which is a method called the trapezoid rule. Today I have my coffee with me. I don't have my usual copper mug or whatever, but the idea is, as long as I don't spill this all over my tablet, that if I ever have to catch my thoughts or um, sneak a look at my notes or whatever, I can do that under the guise of needing a sip of caffeine. So anyway, why don't we jump into talking about what we're going to talk about? We left off talking about Riemann sums, and with Riemann sums, we're approximating the area under a curve, or approximating the value of a definite integral by using a series of areas of rectangles. So we're calculating areas of rectangles defined in different ways and adding them up. Okay. Now, rectangles suck, especially because there are ways that we can just finely tune that sort of strategy in order to do better. And where trapezoid rule comes in is a really simple spin on the concept of a Riemann sum. The idea is this: why use rectangles when other shapes might do a better job? So here's the idea. I'm going to actually take this axis down here and kind of quickly draw some function and hope that my pen doesn't mind the canonical random nice sweeping function that we always seem to use for integration stuff. And I'm going to find a partition for it as if I was going to do a Riemann sum, but I'm going to kind of switch up the game a little bit. So maybe I'll just do 3 rectangles here, or 3 subintervals rather. 1, 2, 3. Okay. And I guess the first one I'm going to put at 0. Okay. What I'm going to do here is try to come up with a simple approximation of this curve, but I'm not going to use rectangles to do it. Here's what I'm going to do. I'm going to use the height right here. Oops. I'm going to use the height right here as well, and go up to the top of the up to the height of the function, and then here as well, and here as well. I'll try to make that. Okay, so rather than define rectangle heights, what I'm actually going to do is connect the dots in order to create 3 trapezoids. Watch what happens. So the first quantity that I'm going to be using in this estimate is going to be the area, oops, of that trapezoid right here. And then the next point, no, don't want to do that. Next one is going to join those two together. See, my ability to draw straight lines on a document camera in front of the class is just much further well developed than this right here. But I'm doing my best. And all y'all will forgive me because that's all I can do right now. Anyway, 1, 2, 3 trapezoids. And those trapezoids are just connecting the heights at the different points. And you can imagine, if I was to use rectangles instead, I'd get a far worse estimate, like visually speaking, than this. So let's see how we would mathematize this process. Let's go to the next page. Okay, so here's what we're going to do. It's very similar to Riemann sums. You start with a partition. You divide up that interval into n subintervals. We're going to define x0 equals a as the, here I'm going to switch to blue to fix it, put in some of these blanks here, as the left endpoint of the first subinterval. And we're going to increase the index until we get to the right endpoint. So we have x0, and then x1, x2, x3, x4, all the way to xn. Okay, so imagine x0 to x5. There would be 5 subintervals. The one between 0 and 1, the one between 1 and 2, the one between 2 and 3, and so on, until I get up to 5. That way, x0 is the left part of the domain of the integral, and the xn is the right, the b. Okay, and we're going to create a trapezoid over each subinterval. And we're going to use the heights of f of xi minus 1 and f of xi. So the height of the function at two consecutive nodes as being the heights that are involved in that the trapezoid associated with that subinterval. And then what we're going to do is simply add up all the areas of those n trapezoids. And that's all well and good, but you know, this is one of those awkward moments where yourself in at the age of 10 or 11 might be much better at this process than yourself right now, because if you're like any normal human being in first or second year, or well, I don't know, most normal human beings, you're not finding the areas of trapezoids on a daily basis. So you probably learned this once upon a time to do some exercises in Mrs. Brown's grade 4 class or something like that, and you've long since forgotten. But trapezoids have a really simple formula. If you think about what a trapezoid um, looks like, I guess on the next page there's a bit of a demonstration about that, right? All of our trapezoids are going to have this sort of flat bottom because we're thinking about an area above an axis or even below an axis, right? And we're going to have two different side lengths or heights, I guess. Here I called them P and Q. If you think about it, the area of that thing is going to be the average of the areas that would be produced by the rectangle created by Q and the rectangle created by P, right? Because it's halfway. It's taking off a triangle that is in between, right? It's halfway between those areas. And that's reflected in the formula for the area, which is just below here. It's a half HP plus a half HQ, right? Or HP plus HQ over 2, which is the area of the one rectangle plus the area of the other rectangle over 2, or the average of the two areas. So that area formula really isn't too hard to remember, but we're going to derive a scheme out of this, okay? I want to think about drawing the heights of the functions, or the height of P and Q defined by the height of the function is what I mean. And that means that for our scheme, the trapezoid between xi minus 1 and xi is going to have area of, let's see, 1 half h, and then we're going to say f of xi minus 1 plus f of xi. That's how I'm going to create any particular rectangle, or sorry, trapezoid's area, and that's the building block that we're going to build this scheme out of. Okay, let's continue onward here. So back to our integral. Considering a general definite integral from a to b of f of x dx, we're going to build a formula that calculates the necessary area over the entire domain of integration. Okay. To try and build a scheme, I thought it would be a good start to think of how we would put together two trapezoids, and from there we can extend and kind of reason out what it would be like to do 3 or 4 or more trapezoids in order to get an idea for how this this scheme works. So let's see here. We have suppose we have the case where we have just two trapezoids. So we have equal width h, and we're defining one between the A and a midpoint. I'm going to call it x1. And then the second trapezoid is going to be between that midpoint and x2, the second one. Okay, and so that's going to give us two trapezoids that fill up the domain of integration from A to B, and I'm just going to use that formula twice. So if I do, we're going to get something that looks like this. The area is going to equal 1 half h, okay, f of x0 plus f of x1. Just by using that formula that we talked about in the last page, this would be the first trapezoid. So maybe I'll write that down. Oops. Let's do that. So area of the first trapezoid. And then I need to add the second one. And the second one is going to look like this. It's going to be plus 1/2 h, and then I'm going to take f of x1 plus f of x2, right? Two consecutive points. And that's what we get, right? The average of the two corresponding rectangles. That's what it ends up looking like in the formula. But I'm going to take that and I'm going to work with it a little bit because it turns out that this, I don't know, it's going to factor down kind of nicely, right? I have a 1/2 h that's common to both terms. So why don't I just pull them out and see what's left? If I do that, I get this, 1/2 h. And then think about what's left over. I have an f of x0, an f of x1, an f of x1 again, and an f of x2. So in fact, we end up with an interesting kind of formula here where I get f of x0 plus 2f of x1, whoops, and then plus f of x2, like that. And the key here that I want you to notice is that this middle point, this middle term, it gets double counted. Because it's involved in the calculations for two different trapezoids. And so we have to consider that in our formula, right? It's going to create a little bit of an interesting thing. So that's what this the blank down at the bottom of the page is about, right? We can see that the heights at the interior node, the height at the interior node is going to get counted twice in this formulation, while the heights at the outer nodes just get counted once. And we're going to have that reflected as we go forward towards a more general formula. Okay, so let's see. Indeed, if you tried to do, more points, suppose you did 4 trapezoids and you had 5 points if you include both boundaries of that domain, then you end up getting that all 3 are interior nodes, and if you work on the formula, all 3 of those interior nodes would get double counted. And in general, if you have n, the only ones that only get counted once are the ones at the outside endpoints, right? The a and the b, or the x0 and the xn, if you want to call it that way. All of the ones in the middle get counted twice, and that's what the formula gets born from, right? 1/2 h times f of x0 plus 2 f of x1 plus 2 f of x2 plus all the way through plus 2 f of xn minus 1, but then the last one is just a regular f of xn, okay? That's how to extend the trapezoid rule forward, and we're going to apply that to an example. And it's an example that goes back to that first special function that we talked about at the beginning of this section, the error function, the one that we lovingly called ERF. So we want to use the trapezoid rule and a uniform partition of 5 subintervals to estimate the value of ERF of 2. Okay, that wasn't actually me trying to figure out what ERF is. I remember it quite well. That was just me wanting to take a sip of coffee because I was thirsty. So let's remind ourselves of what the error function is at the top. So let's go up here and say, recall, the error function of x, which I do want you to know, is 2 over root pi, and it was the integral from 0 to x of, and it was e to the minus t squared dt. It's one of those special functions because we can't actually find that integral using any sort of classical methods. You have to approximate it. And that's what it is. So if I want to know what ERF of 2 is, it's going to involve, well, everything's exactly the same, but it's a function of x. X equals 2 goes in here. It's going to be the value of the integral between 0 and 2 of e to the minus t squared dt, and then multiplied by that scaling factor. That's what we're going to want to estimate the value of. And so that's the integral that we're going to need to approximate. So let's write something to that effect, and then start our work over on the left. So this is what we want to estimate. So we'll need to approximate this integral. And we're going to do so using our brand new tool, our trapezoid rule. So I'm going to take this, I'm going to move to the top on the side, and we're going to see about that. Okay, so let's change to red, because I like doing math in red for some reason. I don't really know why that started, but it just is the way it is. So let's see here. The error function of 2 is going to be approximately equal to, and then we're going to use trapezoid rule here. All right. We need to think about that scaling factor out front, because there is this 2 over root pi, and I don't want to forget. If I just try to approximate the integral, I know myself that I'm likely to just forget about it at the end of the day. So I'm going to build that right in here and put that 2 over root pi right out front. Okay, but then take that integral and approximate it using exactly the formula that we have at the top of the page there. Okay, so we want to have 1/2 h. 1/2, well, what the hell is h? Well, let's see. My h, we have 5 subintervals, and I need to approximate an integral from 0 to 2. So if you think about that, that means I'm subdividing a domain of length 2 into 5. I get 0.4 if I work that out carefully. So maybe I'll write that down in the bottom right, actually. So note that with 5 subintervals, we will need each to have width, and that is, I just got that by taking that domain of length 2, right, 2 minus 0, and I'm dividing that by 5, and that works out to 0.4. Okay, so I'll put that in a little bit of a cloud down here. That's going to be our value of h going forward. And that's what I'm going to use back up here in my calculation. So 1/2, and then the h was 0.4. And then I'm going to want to multiply by a bunch of stuff here. And I want to think about this. It's f at the first point, which is 0. So I'm going to need basically f at 0. And then I'm going to have to add 2 f of 0.4 going across to the next point and so on. And I'm going to keep this up, plus on a second line here, 2 f of 0.8 plus 2 f of 1.2, and you're going across, I didn't give myself enough room. I need a single one of the right endpoint, so f of 2. So this is essentially how we need to do it, okay? That follows the rule from above, and we just need to apply it accurately and make sure that we don't screw up using our calculators. So let's see here. Maybe I'll just do a little bit of simplification on the next line while we do some calculation here. 2's are going to cancel, no problem. That's going to give me a factor out front here of 0.4 over pi, root pi rather. And applying the function, a little bit tedious here, but it's going to work out to e to the minus 0 squared plus 2e to the minus 0.4 squared plus 2e to the minus 0.8 squared, and continue 2e to the minus 1.2 squared, 2e to the minus 1.6 squared, and finally we need e to the minus 2 squared. Remember your order of operations, please, right? When you square those numbers, the minus sign is applied after, really important. But if you work this all out on a calculator and double check it and triple check it and make sure you've got it right here, I get a value here of 0.99425, and you can double check that to make sure that I'm accurate when you get a moment. So that is the estimate. The reason why I'm pretty sure it's okay, if you remember back to our conversation about the error function, it does quickly approach 1 asymptotically as the value of x increases. So this seems like a reasonable estimate of that, okay? That's how it works. It's a pretty easy to use formula. It's kind of funky. It's a little bit different than anything we've done before, but really it's nothing more than a souped up Riemann sum, okay? And as a matter of fact, it does do a little bit better than a Riemann sum, and that's what our last little bit here on the next page will talk about. So the derivation for the error is quite a bit more involved. I looked into it, I thought about it, I figured that it wasn't really something we needed to dwell on because it might take me half an hour to come up with a derivation, but it's something you can research. It may be in your textbook, but it's not hard to find online if you're really interested in seeing where this comes from. Okay, but the error associated with the trapezoid rule approximation is given by this. So it's similar justification for the error we did for Riemann sum last class, but it's m, and m is the maximum value of the second derivative of whatever the function is. Okay. So this error function is only valid if the integrand is twice differentiable. So you think about that a little bit. Most of our functions, or many of our functions, would satisfy this criteria, so we're not super worried. B and A are defining our domain of integration. N is our number of different points that are involved, or the number of different subintervals. So yeah, essentially, if you take a look at this and compare to the error that we talked about last class for Riemann sums, that involved an n on the bottom, and this involves an n squared. So as n increases, you can see quite easily that this value is going to shrink towards 0 more quickly because n squared grows more quickly. So that error is going to decrease towards 0 at a faster rate. And that's what goes in this blank. Okay, so yeah, it is the case, right, where as the value of h, as the distance between those consecutive nodes shrinks towards 0, the error for both the Riemann sum and trapezoid rule both go to 0. Okay, it's just that the error shrinks more quickly for trapezoid rule than for Riemann sums. Okay, actually, I should be precise and say the error that we did last class was for right Riemann sums, and I believe that if you actually use a centered Riemann sum, the error there is also something that converges more quickly. So that's another interesting thing you could investigate if you were interested. Okay, so I just wanted to apply this error bound to our problem from the last page. We can apply it to the previous, ERF of 2, we had 5 evenly spaced trapezoids, so our n is equal to 5 here. Our A and our B were 0 and 2 respectively. And finally, you could show that the maximum of the second derivative of that the integrand, which is essentially 2 over root pi e to the minus t squared, is equal to that 4 over root pi. And what we obtain at the end of the day is that the error, just changing back to red here, if we take for granted that formula from the top of the page, we know that the error has got to be less than or equal to that, that m, which is the going to be this bound on the second derivative, so 4 over root pi, and then b minus a cubed over 12n squared would be 2 minus 0 cubed over 12 times, well, our n was 5, so 5 squared. This is giving us an upper bound, how bad the approximation could possibly be, okay? Is supposing that you don't know the actual value. And if you work all of this out, this is 0.06018. That just gives us a rough estimate for about how bad things could possibly be. And it turns out a lot of the time, most of the time, trapezoid rule does a lot better than Riemann sums, and certainly that error shrinks much more quickly as the number of trapezoids increases as well. So that's where I'm going to leave this lecture. I have one more that I want to produce, and it is on Simpson's rule. And that should be a kind of cool discussion. We will talk about it in my next video. So thanks a lot, and I will see you then.